The lesson is subtle but crucial. With weights, the node that is fewest edges away is not necessarily the closest in true cost. Nearness in hops and nearness in distance have come apart. We need an explorer that expands by actual distance, not by counting steps. This is the leap Dijkstra made in 1956, reportedly while thinking it through in about 20 minutes at a cafe. Instead of expanding in layers of edges, expand in layers of distance. Always grow outward toward whatever is genuinely closest next. That single change fixes everything. To make this concrete, we keep a table. For every node, we store our best-known distance from the source so far. At the very start, we know nothing. So every distance begins at infinity, meaning unreached. Every node except one. The source node is special. Its distance from itself is obviously 0, so we write 0 there. This 0 is the seed of the entire computation. From this single certain fact, all the others will grow. Now picture two kinds of nodes as we work. Some are finalized, their true shortest distance locked in forever. The rest form a shimmering boundary of tentative distances, our best guesses that might still improve. This boundary is the frontier, and watching it move is the heart of Dijkstra's algorithm. To always grab the closest tentative node quickly, we lean on a special container called a priority queue. Think of it as a bucket that, whenever you reach in, always hands you the item with the smallest number. We fill it with nodes keyed by their current tentative distance. So the whole algorithm becomes a simple loop with a clear rhythm. Pull out the closest tentative node, lock it in as final, then look at its neighbors and see if going through it offers them a shorter route. Repeat until nothing tentative remains. That neighbor checking step has a name worth savoring: relaxation. For each neighbor we ask a single question. Is the distance to me through this node I just locked smaller than the best I'd found before? If yes, we relax, lowering the neighbor's tentative distance to this better value. The word relaxation comes from imagining each distance as a stretched rubber band held taut at an overestimate. Every time we find a shorter route, the band relaxes and shrinks toward its true length. It can only ever get shorter, never longer, as the algorithm runs. Let's run the whole thing on a real graph and watch every step. Here is our network of nodes and weighted edges, with the source at the left glowing at distance 0. Everything else sits at infinity, waiting. The priority queue holds only the source for now. We pull the source from the queue, since it's trivially the closest thing at distance 0. We lock it in as final, marking it with a solid, settled color. Its 0 can never improve because nothing is closer than the start itself. The frontier is about to bloom. Now we relax the source's neighbors. Each one's tentative distance becomes simply the weight of the edge from the source, since the source sits at 0. Watch their table entries drop from infinity to real numbers, and watch the frontier ignite around the start. The priority queue now holds several tentative nodes, each with its own distance. This is the key moment. We don't pick the one with the fewest edges, we pick the one with the smallest total distance. The queue surfaces that closest node automatically. Let's pull it. We lock this closest node in, and here is the deep promise Dijkstra makes. The moment we pull a node as the smallest tentative distance, that distance is already its true shortest distance. We will prove why in a moment. For now, trust it and lock it solid. With this new node locked, we relax its neighbors in turn. For each, we compute the locked node's distance plus the connecting edge weight. If that beats the neighbor's current tentative value, we lower it in place and the number visibly updates. The frontier pushes a little farther out. Notice something important during relaxation. Some neighbors don't improve at all, because the route through this node is longer than a path they already knew. In that case, we leave them exactly as they are. Relaxation only ever accepts a strictly better offer. Now the trap snaps shut. The path continues from Y onward to X, adding more non-negative edges, which can only make the total larger or equal, never smaller. So the full secret path to X is at least Y's distance, which is at least D. It cannot be shorter than D after all. The contradiction proves it. No shorter path to X can exist. So D truly is X's shortest distance the moment we pull it. This is why greedy is safe here, and it's why it would fail with negative edges. A later negative step could secretly shrink a path we'd already locked. With that guarantee in hand, we can trust the whole process completely. Let's return to our example and finish the run, locking node after node, each one certified shortest the instant it's pulled. The frontier keeps blooming until it has nowhere left to grow. Finally, the queue empties and every node is locked. The distance table is now completely filled with true shortest distances from the source to everywhere. In one sweep, we didn't just solve one path, we solved them all. That's the quiet generosity of Dijkstra's method. But distances alone don't tell you which streets to actually drive. To recover the routes, we add one small piece of bookkeeping. Whenever relaxation improves a node's distance, we also remember which neighbor we came from, storing a pointer back toward the source. These back pointers quietly weave a tree, rooted at the source, reaching every node by its shortest route. It's called the shortest path tree. Every branch of it is a guaranteed optimal path, all sharing the same origin. Now pick any destination and trace the path home. Start at the target, follow its back pointer to the node it came from, then follow that one's pointer, and keep walking backward. Each hop steps you strictly closer to the source until you arrive. Reverse that trail, and it lights up as the shortest path, glowing from source to destination. Every edge on it earned its place through relaxation. This single luminous route is the answer the whole algorithm was built to deliver. And because we stored the whole tree, we can light up the shortest path to any node at all, instantly, without recomputing. Tap a different destination and a new route blazes to life. One run, every answer, ready on demand. Let's step back and count the work. Each node gets locked exactly once, and each edge gets relaxed only when its source node is locked, so each edge is examined just once. The priority queue does the heavy lifting of finding the minimum each time. With an efficient priority queue built from a binary heap, each pull and each update costs only about the logarithm of the number of nodes. Multiply that across all the nodes and edges, and the total running time grows gently, roughly the edges plus nodes times that logarithm. Even huge networks stay tractable. This efficiency is why Dijkstra's algorithm is everywhere. It routes packets across the internet, plans directions in mapping apps, and guides characters through video game worlds. Almost anywhere a system asks what's the cheapest way from here to there, a descendant of this idea is running. It's worth naming the one real limitation we already met. Dijkstra assumes no edge has a negative weight. If costs can go negative, as with certain financial or physics models, the safety proof collapses and we need a different tool, like the Bellman-Ford algorithm, which trades speed for that extra generality. So here is the whole idea in one breath. Grow a frontier outward from the source, always finalizing the closest tentative node next, relaxing its neighbors as you go. Non-negative weights guarantee that the closest guess is always the truth, and back pointers turn all those distances into the paths themselves. What began as a cafe thought experiment about walking across a city became one of the most quietly essential algorithms ever written. The next time your phone finds the fastest route home, picture it, a glowing frontier, rippling outward by true distance, locking in certainty one node at a time. That's Dijkstra's shortest path algorithm, from the intuition of an expanding frontier all the way to the proof that greedy is safe. Play with it on a graph of your own, add weights, and watch the frontier bloom. Once you've seen it move, you'll spot it working silently behind half the technology in your life. If this made it click, subscribe for more visual math.